There are numerous captivating objects and exquisite phenomena present in the vastness of space. One of these is the Tarantula Nebula, where active star formation is currently occurring. Another notable feature is the largest star ever observed by mankind. In addition, there are mysterious entities like the supernova SN 1987 and the megastar WOG 64. All of these cosmic wonders are located within the galaxy known as the Large Magellanic Cloud. Despite its relatively small size, this galaxy conceals not only the aforementioned objects, but also a plethora of enigmas, mysteries, and secrets. Furthermore, it poses a potential threat to the solar system in the future. So, let us embark on a remarkable journey, my friends. Everything you need to know about the Large Magellanic Cloud will be revealed. While we are on this journey, let us acquaint ourselves with the subject at hand. The Large Magellanic Cloud is situated at a distance of 163 light-years from our location. It is a spiral-barred dwarf galaxy, serving as one of the satellites of the Milky Way. It is important to note that satellites are not exclusive to planets. Due to its unique shape, this galaxy is classified as an irregular galaxy. Its structure exhibits significant distortions caused by tidal interactions with its sibling, the Small Magellanic Cloud, as well as with our Milky Way. In terms of diameter, the Large Magellanic Cloud, or AMC for short, is approximately 1/10 the size of our galaxy, with a mass that is 300 times smaller. Its radius spans around 14 light-years. Despite these proportions, it ranks as the fourth largest entity within the local group, surpassed only by Andromeda, the Milky Way, and the Triangle Galaxy. The Large Magellanic Cloud has been the subject of study for countless centuries, attracting particular interest from navigators during the Middle Ages. For instance, Magellan employed this galaxy for navigation calculations during his circumnavigation of the world, which led to its present-day name. However, it was not until 2013 that astronomers were able to accurately determine its distance. And a little earlier, in 2006, measurements utilizing the Hubble telescope aided in establishing the galaxy's rotation period, which amounts to 250 million years. The Magellanic Clouds, both large and small, formed simultaneously with our galaxy approximately 700 million years ago. The Large Magellanic Cloud raced past the Milky Way at a speed of 327 km, establishing the current distance of 163 light-years, a distance that will gradually diminish over time. Similar to most irregular galaxies, the AMC is abundant in gas and dust, fostering active star formation in its midst. It serves as an astronomical treasure trove, boasting approximately 60 globular clusters, 400 planetary nebulae, 700 open clusters, and hundreds of thousands of giant and supergiant stars. This region is home to more than 30 billion stars, offering a visual feast for the eyes. The Large Magellanic Cloud harbors extraordinary celestial gems, such as the massive star WOG 64 surrounded by a torus of gas and dust, as well as the brilliant hypergent known as the Golden Fish, located in the northern region of the AMC. If this star were positioned in place of Proxima Centauri, the closest star to us, the Earth would never experience darkness. Of particular scientific interest is the uncommon dynamics present in this ancient galaxy, which accompanies the birth of new stars. The Large Magellanic Cloud exhibits a plethora of young stars, surpassing even the youngest stars found in the Milky Way. The Tarantula Nebula serves as a hotbed for active star formation, acting as a true stellar nursery. Let us briefly pause and examine this phenomenon in greater detail, as the Tarantula Nebula possesses distinct characteristics. But first, what exactly is a nebula? It refers to a section of interstellar medium that stands out from its surroundings either by emitting radiation or by absorbing it. Initially, in the field of astronomy, nebulae encompassed any extended objects within deep space. Only later, with advancements enabling accurate identification, did the term nebula acquire a more precise definition. Nebulae predominantly consist of accumulations of dust, gas, hydrogen, helium, and plasma. Various types exist, such as the Coal-Sec Nebula, which is a dark nebula containing dense formations of interstellar gas and dust that absorb light completely. Reflective nebulae, on the other hand, emit light due to the reflection of cumulative radiation scattered in the stellar dust surrounding bright stars. Nebulae generated by shock waves, resulting from explosive matter ejections during supernova explosions or stellar winds from Wolf-Rayet stars, are also observed. Emission nebulae are clouds of ionized gas emitting intense radiation in the visible range, with ionization predominantly caused by high-energy photon fluxes from young stars with high temper. We refer to it as tarantula due to its resemblance to the famous spider. The tarantula spans a length of 700 light-years. The entire area consists of ionized hydrogen. Its distance from us is 179 light-years. Imagine if we were to replace the tarantula with the Orion Nebula. Not only would it be visible to the naked eye in the night sky, but it would also appear 55 times larger than the full moon. Within the nebula, there are 800 stars, including recently formed protostars that are still encased in cocoons of space dust. The central part of the nebula is home to a small yet incredibly bright cluster called R136, which emits the majority of the nebula's glow. Within this cluster resides the most massive and brightest star known to science, R13601. This giant star surpasses the Sun in mass by 265 times. The brightness of this area makes it an ideal location for studying the processes of stellar evolution. In 1987, a supernova erupted on the edge of the Tarantula Nebula, shining so brightly that it was visible to the naked eye from Earth. It was later named SN 1987. This supernova originated from a blue supergiant star with a mass 17 times that of the Sun. Its occurrence had a significant impact on our understanding of stellar evolution, leading to revisions of various theories. Prior to this event, it was believed that supernova explosions only occurred in red supergiants and Wolf-Rayet stars. Further observations in X-ray and gamma-ray wavelengths unveiled the mystery of SN 1987. It was revealed that it began with a merger of two stars, one large and one relatively small, resulting in a rapidly rotating blue supergiant. Recently, images captured by a network of radio telescopes in the Atacama Desert discovered signs of a young neutron star in the remnants of the supernova. The pulsar is still surrounded by dense layers of clouds, but in the coming decade, they will dissipate, allowing direct observation of the radiation emitted by the neutron star. In the future, our descendants can expect astounding changes in the astronomical landscape. As mentioned earlier, the Large Magellanic Cloud is under the strong gravitational influence of our galaxy. In approximately 5 billion years, the Milky Way will commence the absorption process of the OMSI. This collision will awaken the dormant black hole Sagittarius at the center of our galaxy, potentially increasing its size tenfold and even transforming it into a powerful quasar. However, these outcomes are still subjects of debate. What does this mean for the future of Earth and its inhabitants, if any remain by then? It is likely that the planet's inhabitants will witness a magnificent cosmic display of high-energy radiation emanating from the vicinity of the black hole. Some astrophysicists also predict another outcome: the expulsion of the solar system from the galaxy. Following that event, in about 1 billion years, Andromeda will begin the absorption process of the Milky Way. Exciting times lie ahead. Hopefully, by then, the inhabitants of Earth will be prepared for the collision and, if necessary, take measures to ensure the preservation of our species. In the meantime, we can marvel at the Large Magellanic Cloud as a beautiful object in the night sky. The easiest way to locate it is by drawing an imaginary line between the stars Sirius and Canopus, as the galaxy will be positioned near this line. However, it can only be observed from the southern hemisphere. So, if you plan on visiting South America or Australia, you can admire the galaxy and even capture a stunning astrophotograph as a keepsake for future generations. Black holes, concealed celestial objects contrary to their name. Black holes are not truly black. They represent regions in space where gravity's pull is so intense that even light, the fastest entity in the universe, cannot escape. As a result, black holes are deemed invisible. Despite their inability to be observed directly, we can infer their existence through various methods based on their characteristics, which we will explore further in this article. For centuries, scientists have grappled with unraveling the identity of black holes. In 1916, Carl Schwarzschild discovered the first modern solution of general relativity that described a black hole. However, it was not until David Finkelstein's publication in 1958 that it was interpreted as a region of space from which nothing can escape. The formation of black holes are born from the remnants of massive stars. Stars with a mass greater than 3 times that of our Sun have the potential to form a black hole. Stars begin their life as hydrogen atoms, collapsing from immense gas clouds due to their own gravitational force. Through nuclear fusion in their core, hydrogen atoms combine to form helium, generating heat and radiation that counterbalance gravity's pull. A delicate equilibrium between these opposing forces is required for a star to survive. In the core, helium fusion can further progress to heavier elements such as carbon, oxygen, neon, silicon, magnesium, sulfur, and iron. However, iron cannot undergo fusion, leading to the cessation of radiation and heat generation. With the internal pushing force absent, the balance is disrupted, causing the star to collapse under its own gravity. Within a fraction of a second, the core becomes densely packed, merging protons and electrons to form neutrons. The core's temperature soars to billions of degrees, resulting in a supernova explosion. The leftover core material can then form either a neutron star or a black hole, depending on the mass of the original star. The size spectrum of black holes exist in various sizes, categorized as follows: primordial, miniature. These are the smallest type of black holes, with sizes comparable to a single atom but possessing the mass of a large mountain. Stellar black holes are the most common medium-sized black holes. Their mass can be up to 20 times greater than that of the Sun, fitting within a sphere with a diameter of approximately 10 miles. Intermediate. This category includes black holes that are larger than stellar black holes but smaller than supermassive black holes. Supermassive black holes are the largest known black holes. Their mass can exceed that of 1 million suns combined, and their diameter is comparable to the size of our solar system. It is widely believed that every large galaxy harbors a supermassive black hole at its core. Understanding black hole types: there are 2 primary types of black holes, non-rotating and rotating black holes. Schwarzschild, non-rotating black hole. This type of black hole, often referred to as a Schwarzschild black hole, features a singularity and an event horizon. The singularity represents the center where all the star's mass is concentrated, characterized by infinite density according to general relativity. The event horizon, on the other hand, denotes the boundary beyond which matter and energy cannot escape the gravitational pull. Kerr, rotating black hole. Rotating black holes, known as Kerr black holes, possess the intriguing characteristic of rotation. This rotation introduces additional components that facilitate the study and comprehension of black holes, making their discovery relatively easier. Components of a rotating black hole include singularity, located at the center. The singularity represents the point of infinite density where all matter and energy. Here's the continuation of the previous response. Singularity, located at the center. The singularity represents the point of infinite density where all matter and energy are concentrated. In a rotating black hole, the singularity takes the form of a rotating ring or disc-shaped singularity, known as a ring singularity or a Kerr singularity. Ergosphere, surrounding the rotating black hole, there is a region called the ergosphere. In this region, space-time is dragged along with the rotation of the black hole. As a result, objects within the ergosphere are forced to rotate in the same direction as the black hole. The ergosphere plays a crucial role in extracting energy from the black hole through a process called the Penrose process. Event horizon, similar to the non-rotating black hole, the rotating black hole also has an event horizon. It is the boundary beyond which nothing, including light, can escape the gravitational pull of the black hole. However, the event horizon of a rotating black hole is slightly different from a non-rotating black hole and is referred to as the static limit. Inside the static limit, space is dragged by the rotation of the black hole, affecting the movement of objects and light. Accretion disk. Around a rotating black hole, matter from its surroundings can form an accretion disk. The accretion disk consists of gas, dust, and other debris that is gradually pulled into the black hole due to its strong gravitational force. The material in the accretion disk heats up and emits intense radiation, making it visible to observation. Studying black holes. Since black holes themselves are invisible, scientists rely on indirect observations and theoretical models to study them. Some methods used for studying black holes include 1. Observing accretion disks. By observing the intense radiation emitted from the accretion disks around black holes, scientists can gather valuable information about the presence and properties of black holes. Different wavelengths of light, such as X-rays and radio waves, provide insights into the behavior and dynamics of matter falling into the black hole. 2. Gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects. The detection of gravitational waves from the merger of black holes has provided direct evidence of their existence and has helped to determine their masses and properties. 3. Effects on surrounding objects. The gravitational pull of a black hole affects the motion of nearby objects, such as stars or gas clouds. By studying the motion and behavior of these objects, scientists can infer the presence and characteristics of a black hole. 4. Simulations and theoretical models. Scientists use computer simulations and theoretical models based on general relativity to understand the formation, behavior, and properties of black holes. These models help to predict and explain various phenomena associated with black holes, such as the dynamics of accretion disks, the emission of jets, and the evolution of black hole mergers. Black holes continue to be a fascinating subject of study in astrophysics and cosmology. Through ongoing research and technological advancements, scientists hope to uncover more secrets about these enigmatic cosmic entities and expand our understanding of the universe.